If you are new to the channel, then subscribe the channel and press the bell icon for further notification. Okay student, welcome you all to this new lecture in Gate Power System series. So today again we will be solving 5 questions starting from question number 46 to up to question number 50. Okay, then let's try to solve these questions. Okay, in question number 46, the voltage phasor of a circuit is given this much, the current phasor is given this much, the active and reactive power of the circuit is. So if voltage phasor, current phasor is given, then complex power you know S is equal to VI star. So which is equal to P plus JQ. So V is given 10 angle 15 and then multiplied by I star is 2 star, that's why it will be plus 45. That is your P plus JQ. That is at par as per our load condition. Okay, so if you go this one, then 20 at an angle of 60. So it will be 20 cos 60, 20 sin 60. So it will be 10 plus, if you do sin 60, then it will be 17.32 J. So that means P equal to 10 kilowatt and Q equal to 17.32 watt, kilowatt. Or not kilo, only watt and only watt. So that is your option A. Now if you come to 47, the transmission line has equal voltage at two ends, maintained constant by two sources. A third source is to be provided to maintain constant voltage equal to the end voltage at the either the midpoint of the line or at 75% distance from the sending end. The maximum power transfer capabilities of the line in the original case and the other two cases respectively will be in the following ratio. So suppose you have a transmission line. So this one, this side sending end voltage and this side receiving end voltage. Suppose this is V1, if I say this is V2. They are at fixed at a same voltage, that is suppose V, they are fixed, and suppose this reactance is line reactance. So one case it is at midpoint, this is one case, and another case it is at 75% distance from here. So you can think of 75, 50, then it is 75%, it is at 50%. Okay, what is the initial power transfer capability? Initial power transfer capability is V1, V2, that is V square by X, whatever this sin delta is, the angle between that two. Or maximum power that can be transferred, or then sin delta you will consider at 90, so it will be V square by X. So that was the maximum power transfer capability from here to here in the original case. Now if you come to 50%, this will be X by 2, this will be X by 2. So both will be equal. So whatever power here also, then the voltage is V, magnitude is V. So whatever power you have from here, it can be transferred to here, the same power you can think of. So let me see how much power I can transmit to here and how much power I can transmit to here. Both will be same because both are X by 2, you can see. So here P max will be, you can take either this X or this X, same power. Whatever you transfer here, the same amount you can transfer this side also, because it is X by 2, you can see it. So it will be V square X by 2, or it will be 2 into V square by X, something of this fashion. That is twice the first one. This was the first case, P max 1, P max 2, now P max 3. Now in the third case, this reactance is, this X will be, because it is 75%, so it will be 3X by 4 and this will be X by 4. Now whatever power you can transfer here, the same power you cannot transfer here, you can see. The reactance here is more, the reactance here is small. So more reactance is whatever power you can transfer here, here you can transfer more power than that one. You can see there will be two cases. So let me see first how much power I can transfer here, then I have to see how much power I can transfer from here to here. Whichever is minimum, that will be my case, because if I can send 200 here, but if I cannot send 200 from here, if I can send only, suppose this from here to here I can send 200 megawatt, from here to here I can send 150 megawatt. So how much I can save from here, send from here to here safely? 150, because 200 will come here, but 200 I cannot transfer. So the power I cannot transfer maximum power from this to this side. So you have to think now. So here it will be V square by 3X by 4 and here it will be V square by X by 4. So it will be 4 by 3 V square by X and it will be 4 V square by X. So whichever is smaller, this one is the smaller. This one is 4 times, this one is, that is 4 by 3 times. So obviously this one is smaller. So this much power I can transfer. Here I can transfer more, but no use, because I cannot transfer that much power from this side. So the power transfer capabilities will be this one. So this is to this is to this. That means 1 is to 2 is to, and this one they have written is I think 1 by 1 say 0.75. Because 3 by 4 is 0.75, so it is 1 by 0.75. That is 1 is to 2 is to this one. That is option B. It should be B. Now if you come to 48, a lossless radial transmission line with surge impedance loading. So if it is a surge impedance loading, means total reactive compensation is reactive power delivered or reactive power absorbed in the transmission line is 0. Whatever is, you can say, absorbed by L will be supplied by the C of the line. So they mutually cancel each other. So there is no reactive power requirement for the transmission line to give externally, or it is not taking any reactive power from the source, or it is not delivering also. The transmission line, inside the transmission line, whatever it is absorbing by L, transmission line inductance, that is provided by the C of the transmission line itself. So they mutually cancel each other. So reactive power compensation is not required. Reactive power, it is not delivering also, it is not absorbing also. So if it is so, it becomes and if you loaded it surge impedance loading, that means that one. So that power factor becomes unity power factor, because it will look like a pure resistive load. So power factor will be unity, and it is a lossless line, so there will be no voltage drop along this line. So that is a flat voltage profile. So voltage profile will be flat. Everywhere the same voltage will be, it will be same voltage. No drops will be there because it is lossless, and also all the reactive powers are compensated. So no X will come. Whatever X drop will come in L, same X in capacitance drop will come, and it will compensate each other. So it will be a flat voltage and unity power factor at all points along it. So that is the idea of SIL in a lossless transmission line, that is C. Now if you come to 49, consider the model shown in the figure in the transmission line, series capacitor at its midpoint, the maximum voltage of the line in the location. So here you can see Vs is 1 angle 0, I is also, power factor is given 1. So I is, that means in the same phase with the Vs. Okay. That the same I is flowing in through this line. So if you take this one in normal phasor diagram also, you can analyze this one. Suppose this is my Vs, so my I will be somewhere here. So the first drop, that is inductor drop. So inductor voltage, you know, it will be, inductor case I should be lagging, so your voltage should lead. So it should come somewhere here, J1, J.1. X into I is 1, so 1 into this is 0.1. Okay, so this will be your Vp2. At P2 positions, this will be your voltage. Now if you come to P3, what drop will be added now? There will be now minus J, because it is capacitor now. So it will be, drop will be now below, because current should lead, but it will be from here. Now the voltage is here. From here it will be a drop of minus 1.5 below. So it will come up to this much only, half of this one, because this length is J1.5. So it is actually minus J.5. So here it will be your Vp3. Now again if you go to this one, again it will be plus 0.1 to upside. So from here it will go plus 0.5. So from here it will go plus 0.1, means here. Now this is plus 0.1, the last one. Now it will be up, because it is inductor now again. So if you add now, this is Vp4. Now you can see which one will be the higher voltage magnitude. You can see the maximum voltage of the line at this location. So obviously this one will be the higher, because all are hypotenuse. So this is your base, this is your height. So base is you can see base is fixed for everywhere, but height is maximum here. So if height get maximum here, your hypotenuse will be maximum also here. Here also these and these are equal, Vp3 and Vp4 magnitudes. So it will be obviously option B. And if you come to 50, the balanced delta connected load of 8 plus 6J per phase is connected to this. If the input power factor is to be improved by 0.9 by connecting a bank of star connected capacitor required. Okay. Initially the load was delta connected. So this was the load, my suppose. So this is the load, initial load, whatever the load is, that is 8 plus 6J. And here you are connecting a star connected capacitor to improve it. What is your intention? How to you want to improve the power factor to 0.9? So the input power factor is to be improved to 0.9. So there are so many ways you can do it. This power factor, what is the initial power factor, you can calculate from here. That is the initial power factor. Now you want to go to new power factor. Let me calculate from the Z itself. If Z is given, then from Z itself the power factor can be known. So this was the initial Z. So Z was 6 plus 8J. So initially your power factor was 10, 5 was 8 by 6. 8 by 6 from the impedance triangle Z, R, X. So this was your initial power factor. Now you want to improve it to a new power factor, that is 0.9. Okay, whatever it is, let it be. So now suppose you have a given capacitor here. So capacitance is, if I take admittance, that will be good for per phase. We calculate either you convert this star into delta or you convert this delta into star, whichever you feel comfortable. Then you can compare these two. Suppose if I convert this delta into star, equivalent star, so you know the same. Suppose this is converted, you know which one is converted, these deltas are converted. Now it is looking like capacitor is there, and also the loads are also coming here. These are the loads. This one is converted from delta to star, so this one they are coming in parallel with this here. Now this is the picture. I am converting this outside delta also star, so this is just forming a star. So what will be this value? If I know delta is compact, so if you open it, it will get reduced. So Z will be 8 plus 6J divided by 3. You can remember it this way. And this is 1 by J omega C. Now to calculate it, Z parallel combination, because it is parallel, I am going for Y. So Y will be 3 plus 8 plus 6J plus J omega C. So if you multiply by 8 minus 6J denominator to segregate real and imaginary, divided by 8 square minus 6 square, I think you can do it. A square minus b square plus it will be plus here 10. So if you do it, it will be it will be 10. So it is 0.24. It will be 100. It will be 10. 6 square 8 square will be 100. So 24.24 minus 18, that is 0.18 j plus j omega c, which will be equal to 0.24 plus j if I take common omega c minus point. Now this one is y, new y. So new z, suppose it is r new x new. Suppose new z angle is z angle theta new. So if you take y new, what will be this angle? Z 1 by z new, and angle will be minus theta new. That angle. Okay. So you can think that if you convert z to y, that the angle gets negative. That you have to be very careful, because I have taken y. So that negative you have to take. But this angle is given to you. This is what? Tan inverse 0.9. Because the power factor is 0.9, that is nothing but power factor angle. So if you calculate, cos inverse, power factor is given 0.9. So it is 25.84. So this angle is given. So what is the angle? If you convert it this one, if you want to find the angle of this one, this is nothing but tan inverse omega c minus 0.18 by 0.24. That should be equal to minus 25.84. That is my idea. This minus, you have to be very careful why I am giving this minus. Because this angle, this theta was the power factor angle, which was the angle of z, not y. So if you convert it into z, that angle gets minus theta. If you inverse this z, so 1 by z, angle get inversed, that is minus theta. So that you have to be very careful, this minus. I am again mentioning it. So this is very important, this one. Tan of this one will give you some minus 0.48. Now you can easily do it, I think. It will be 0.24, it will be minus 0.4843. So if you do it, you will find your omega c will come around 0.0637. Now this is xc, this is y, you can see, per phase. This one we have calculated per phase. Okay. If the input power is to be improved by star connected capacitor, the required kVAR of the bank. So entire kVAR of the bank, not capacitance they are asking. So kVAR. So kVAR means total kVAR. Okay. So if you calculate per phase, so it will be Q per phase will be equal to V per phase V square omega c, because I have calculated it is per phase. So this is also per phase. So Vp per phase, it is 400 by root 3 whole square into this one 0.0637. So whatever you got, this is per phase. So total Q will be 3 into Q per phase. So 3 into whatever you got. So your answer will be 10.2 kVAR. That is your option B. If you like the video, then press the like button and please give your valuable comments in the comment section.